Again, I'm Keita Teranishi from Oak Ridge National Laboratory. So this session is going to be 5 speakers going to be presenting programming model programming systems, to talk about, discuss about the position and try to make a provocable discussion. And we have 5 speakers, and I'm asking each speaker to introduce, introduce just for 2 to 3 minutes. So the first speaker is Brad Chamberlain from HP Enterprise again to talk about the Arcuda and Chapel. Please.
Great, thanks. Well, you've already heard from me today, and we have a lot of great panelists up here. So I'm just going to give you a quick reminder that I told you about 2 things today. There's Arcuda, which has this client-server model where the client is in the Python world. Server happens to be running over Chapel on a supercomputer. That gives us massive scalability and performance that allows us to outperform Dask and Spark, and that there are ways to learn more about Arcuda if you're interested. And again, Arcuda runs over Chapel today, which again is an open source portable programming language we've been developing, now under the Linux Foundation. The Chapel is very productive in terms of supporting concise codes that perform competitively with MPI plus X. It's being used in a wide variety of applications, and it's got a vibrant community with lots of ways to interact with us. So that is just my reminder. And with that, I'll turn it over to the next speaker.
Thank you. So the second speaker is Manolis Papadakis from NVIDIA, and he's going to talk about Kupai numeric.
Hi, thanks for having me here. So yes, I'm representing the Kupai numeric team, which tries to provide a distributed accelerated backend for the well-known NumPy API. You just write your code, and if you do happen to have a million by million matrix multiplication, then we just take care of splitting the arrays, doing the decomposition for you, and then you can launch it through MPI run or whatever launcher, and you allocate your nodes, and we manage we take the single script, and we do the partitioning for you and the data transfer, and your program looks sequential, runs distributed in the background. So yeah, the vision is that you prototype on your local machine, but the same code can scale to CPUs, multi-CPU, multi-GPU, multi-node, and the motivation is to do science without needing to spend time using explicit parallelism APIs. So same as everybody in this panel, I suppose. Yeah, so NumPy and expanding to other libraries. The Kupai numeric is built on top of the Legate platform, which provides the basic primitives to build these different libraries and make sure that they all work together. So we have the common distributed data format that includes information about distribution partitioning that the runtime knows about and can share data between libraries, knowing if repartitioning is necessary, and if it is, then what is the minimum amount of data that needs to move, and decides things for you, like how many of the GPUs to use, or even if to use, if they want we need to use GPUs, if it would be a good idea or not, manages your synchronization, data movement, and everything. So as a layer to build up these different libraries that we're trying to implement that would target well-known productive APIs, and have distributed implementations that work together. So that's.
Then the third speaker is Coin Wall from HP Enterprise, and he presents a Dragon HPC.
Okay, that's. I don't understand why this is suddenly different. Okay, we're going to start. Almost made it.
Yeah. It's the whole part. Okay. Yeah, thanks for having me. So I'm here representing the Dragon HPC project. In one sentence, the aim of the Dragon HPC project is to accelerate distributed Python workflows. There's a few different APIs here. This is not all the APIs, and I'm only going to touch on a subset of these, but feel free to ask questions about any of these if they catch your attention. So the first one is that's kind of important given kind of what we've seen in talks today is multiprocessing API. This API takes Python's multiprocessing and Dragon provides essentially a multi-node backend. So any analysis code that is using the Python multiprocessing API can now span nodes on a supercomputer. Second one I'll touch on that's really important, I think, to the Dragon runtime is the data API. This has the Dragon distributed dictionary. The distributed dictionary is a distributed key value store. So key value store, but backed over the number of nodes in your allocation or whatever subset of nodes you want that data to live on. It looks and feels a lot like a Python dictionary, so it's really easy to write to. The data API also has a C API for that distributed dictionary. So if you want to do communication between like an MPI job that's written in C, C++, and some PyTorch training job, that's a good way to exchange that data. The last one I'll touch on is the workflow API. There's been so much talk of multi-system workflows today, and inside of the Dragon workflow API, there is this proxy API, and it's Dragon's attempt at doing these implementing these multi-system workflows. A couple more things about Dragon. It's optimized for HPC environments, scales to over 2,000 nodes. It's open source pip installable with a little bit of configuration if you're going to use be on one of these supercomputers. It supports HP Slingshot, InfiniBand, Ethernet networks, supports all the kind of common GPUs, and runs on your favorite and least favorite workload manager. So, thanks.
Then the fourth speaker is Johannes Velasco from NORSC, Berkeley National Laboratory, and his position is Julia.
All right, I think my slides are not about Python, so I'm allowed to, be the feisty end to the day. And I think this is, I used to solve PDEs for a living, and I still bemoan the death, well, not the death, but the fact that I don't get to start arrays at 1 anymore. And so really, we're all friends, but a panel needs to be feisty. So if there's one thing I want people to take away from this, it's when someone talks about Pythonic code, it really grinds my gears. We're here to solve science problems, make the code reflect my science problem. Don't make me worry about why particles interacting needs to also be Pythonic. The other thing really is not everything needs to be a effing for loop, right? we have parallel data work items. Why do we keep secrets from our compiler by pretending it to be a sequential thing? And then we have to write these weird little headers to reintroduce into the compiler the secrets that we have kept from it. So here's the OpenMP version. In Julia, you can just sort of say, well, first I'm going to square every element. That could even be dot, whatever. But yeah, there's a even more nicer syntax here, but I like this one for personal reasons. Then we reduce it, or for example, we just use a pipeline. And then, and the reason why this all, oh yeah, by the way, just want to say there's no Julian way of programming. And then Julia also is sort of out of the box. The way the language is built is it creates an ecosystem where scientific, especially parallel scientific work is naturally expressed. And my favorite bit as a software developer is together with compiler toolchain, it really is maybe the most powerful LLVM front end that you can find out there. And oops, the graph doesn't show. There we go. So ultimately, as a scientist, why should you care about it? Well, you can do this in Python, but then you have to worry about your, for example, your loss functions being sort of array-ish. You know what I mean? Everything has to be an array, because in Python you overload the array class. Well, in Julia you make use of multiple dispatch and just-in-time compilation. So the stuff here can contain if statements and so forth. And just by simply moving your array to a GPU, you get the sort of scaling behavior that you would expect from putting this example workload on a GPU. And I want to drill down a little bit more in how this actually works. You might have heard of multiple dispatch. So basically in Julia, you can put into your function declarations type annotations. This basically just says, here I have a matrix A, and it is so I've got two inputs, and one of them is a transpose of a matrix. And then later, the mathematician who's actually implemented this can create a transpose matmul function that is really just the same gem, but we've gone and swapped things around. And so simply because of the type annotation, does the multiple dispatch follow the different code path to the optimal code. And I am almost done. I just want to say, because of some of the things I've heard here, I want to finish with a warning about the glue code pattern. And that is, if your glue language is slow, then you might not notice that crossing the language barrier is expensive, for example, by making type transformations. And so here's a benchmark I ran a while ago in comparing PyBind 11 with Julia's ABI compatible C call, and you get rough anywhere between 40 to 100 times speed up. Now, this can be a problem if your ultimate goal is you want your inner loop to call an AI, right? So even on the same node, you're going to incur a cost. And so that's sort of my final statement. So happy to have a friendly fight with them.
So the last panelist of this session is Ryan Fried from PNNL, and he's positioned with Rust.
Great, thank you. Yeah, thanks for having me. Like you said, my name is Ryan Fries. I'm a senior computer scientist at PNNL. I've also been leading the Laminar project since around probably spring of 2019. So it's fairly new still. The language itself is fairly new. It only went into version 1.0 in like 2015. So we're not too far behind the language itself. Today's been great because this is a lot of background and things I'm very interested in. Runtime systems for the panel, data movement frameworks, not related to this talk, but I've done some work implementing a distributed caching system specifically for a high energy physics experiment called Bell 2, but I think it's pretty applicable to a lot of the topics we were talking about today. And then some performance modeling and HPC resource allocation. So I think a lot of things that other folks are interested here also capture my interests. Whenever I talk about Laminar, I always kind of lead with this question of why Rust, or maybe what Rust is. It's a modern systems programming language, so a bit lower level than what we're talking about with, say, Python and even Julia. And it's really somewhat built as an alternative to C and C++. I won't necessarily say we should, or maybe I should say, since it's a panel, that we should replace C and C++ with Rust. I think really what my position would be is when we're thinking about new projects, let's think very heavily about whether we want to go with an unsafe language like C or C++ versus, can we actually leverage one of these safer languages? And I think Rust is one of those. In part, what's special about Rust? Okay, it has three pillars. One's reliability with respect to memory and thread safety. It comes with very strong compile time guarantees, where if you do something incorrect, the language doesn't like, as in, you're accessing data from multiple threads simultaneously, your program just won't compile. And that's a very nice feature from the language itself. Second, it has very good performance. There's no garbage collection or runtime, and there's zero cost abstractions. It's competitive with C and C++ and in many different applications. And then finally, from a productivity standpoint, and maybe think about this as productivity from a C or C++ programmer's point of view. The cargo build tool is just a pleasant thing to work with compared to whatever you do in C and C++, which isn't anything. And then the other thing that you do there would be the compiler messages. If you've never done pair programming, just try to build a Rust program, and the compiler will essentially guide you with what you did wrong and how to fix it. And that's quite the different experience compared to looking at 50,000 lines of a template error when all you missed was a semicolon. So that's about it for Rust. For Laminar, so Laminar is a distributed tasking, asynchronous tasking and PGAS runtime that's written on top of Rust. This really started out as an experiment of seeing whether we could do something productive in Rust on HPC. We're convinced that you can. Some of the programming abstractions that we're exposing are active messages or remote closures. That enables us to do this thing called a DARC, which is a distributed atomic reference counted object. And this is where we can build out all these parallel data structures that are distributed, where the runtime manages the lifetime of the data, how things are accessed with it, with guarantees about who's touching data at any given time, relying on the language to not compile when it disagrees with what you're doing. And then an example of something that would be a high-level data structure is this laminar array, which is, as you can guess, just a distributed array that provides some nice APIs to do things either aggregated, in parallel. The other kind of thing that we've been really focusing on Laminar is to adhere to a lot of behaviors that the Rust community itself adheres to. So we've tried to, I'm going to say in a rustic fashion, try to integrate with a lot of that. So Rust has a very nice community of third-party libraries, and we want to play very nicely with those, to the fact that you can pretty much just add those to your dependency lists and they'll just kind of work with Laminar, which is nice. We support InfiniBand right now, working to get up and running on Slingshot. And we kind of, have a lot of variability with how we can run on the underlying hardware with respect to processes and multi-threaded. We want to hide that from a lot of kind of higher end users, but we're not quite to that point to where we have the nice Python interfaces yet, although we've done some interesting experiments trying to, follow kind of in Brad's footsteps and play underneath our CUDA a little bit. So we have some proof of concepts there, but with that, I'll kind of get ready for the panel. And I guess the one last controversial thing I'll say is most programmers aren't as good at safe programming as they think they are. So let's just let the compiler do it for us. Yeah, thank you.
All right, so let's start the discussion. And I have a list of questions, but before doing this, I'd like to maybe ask audiences to bring questions. Do you have any?
Well,
Lally?
I don't know, just after the first three talks, there seemed like an obvious challenge amongst the first three. Can we somehow get a competitive, some kind of little informal competition going with results due by SC or something? On some Python, scalable computation that everybody thinks they can handle. And sounds like maybe if Laminar is willing to go under Arcuda, you could do that too.
I think we're a ways away from that still.
Julie,
but yeah.
sorry, it just seemed like an obvious thing after those talks. Does that make any sense, or is that just not something we can do?
What's your algorithm?
Well, so that's the thing. I think you guys have to come to an agreement on what's fair, because I could see it being biased. I could see it being biased, right?
Well, there's also often the problem in HPC, which is every bake-off ultimately ends up being matmul.
Ends up being
every sort of bake-off, every competition ends up being just a big ass matmul.
matmul, right?
And in
right.
the end, all of us would call to the same hyper-optimized matmul library.
Good point. That's a
So
very
it
good
needs to
point.
be some,
Aren't you a code generating, compiling your math?
yeah, but if you do a gem, there's no, I mean, like, if I do a
I'm
gem.
just
on it,
saying,
yeah.
Right, you gotta do
Smooth
something a
and
little
do-
hard. So look, it's a thought. I don't know, we don't need to rat hole on it here. It maybe it's something to discuss at dinner or something to see if that makes any
It's an
sense. I just thought I'd
intriguing
throw it
thought.
out.
I would say that the Julia CodeGen beat the Fugaku vendor library for gem. But NVIDIA, not so much.
You have a lot of people working on gems.
Any comments?
I mean, I love bake-offs. I think they are hard to set up in a fair way. And so often what happens is like, you end up with like 13 things you need to do or 15 things you need to do, and there's a level of effort required. I think our community doesn't do enough of them. One of the bake-offs I like outside of HPC is the computer language benchmarks game. It is by no means perfect, but it is fairly small pieces of code that exercise fairly interesting things like speed of memory allocation or speed of big ints or various things. And it's a very open framework where you can submit things, they'll be measured. You can submit other things like, maybe I don't have the best implementation, maybe you've got a better idea. And it's very democratic in that sense, but it requires someone dedicated to running it and serving as a neutral party. And particularly in HPC, that gets tricky because it's like, well, which hardware do we run on? Or do we run on multiple hardwares? And
Where do you get the resources to do this? Ted?
exactly.
Yeah.
I think it's something our community is lacking and has been lacking. In fact, early in the HPCS project, when you and I first met, we proposed building exactly this kind of thing, and it got a little bit of interest, but didn't get very far.
But not enough money.
Yeah, right. But we're all good at talking up our own stuff. We don't have very many neutral arenas to really pit them against one another, I think.
And I'll say, actually, at supercomputing this year, in the alternatives to MPI workshop, there is a paper that's, I wouldn't necessarily say, well, it's kind of a bake-off, actually. With some of the folks from Chapel, we compared against Lamilar, Chapel, OpenSHMEM. Now, admittedly, Lamilar doesn't perform as well, but because of one of these issues that crop up where we have really targeted libfabric underneath as our fabric provider, as our communication interface. SHMEM, and in InfiniBand, UCX performs significantly better than libfabric. So this is actually this paper that we wrote contributed to us implementing some UCX support. We don't have the results published with that support, but that just goes to highlight like how difficult it is to be fair, because we presented results for the other frameworks using their most optimal way of, gathering their results, where if we all compared on libfabric, Lamilar looks a lot better, but that's not really fair to those other frameworks. So, so there is a little bit of a bake-off there, but.
Yeah.
That was on sorting, right?
Yeah, that was on, I think you even mentioned that sorting maybe. That was
a different sort.
Oh,
but
okay.
Yeah. We have a couple sorts.
Okay, anyhow.
So I'm wondering if you can talk about what foot guns exist in your respective models. So as a bit of background, I've been using CuPy numeric recently for an application I've been writing. And I think in the process, there's this code, pre-existing code. I don't get to choose what it does. I'm just responsible for implementing it. But in the process of writing this code, I've submitted something like a couple dozen issues. Things that didn't work, things that didn't perform, things that weren't implemented, things that crashed, or, so on and so forth. And some of those are just bugs. You fix the bugs, it's, good, great. But some of those are things that, influence the way you write the code. Like, because of this limitation, I can't write the code in the way that I would expect. Or, this isn't as easy to use as I'd sort of hope it would be. And so I think a lot of the systems here are things that would like to be easy to use, but we've got a user community here that isn't that like they're not all computer scientists. They don't have, backgrounds in high performance computing. And so that ease of use really matters. Like, I'm going to go hand off my code to somebody, they hit a bug because it didn't integrate with the job scheduler, whatever, right? And their impression of it is, wow, this thing is really hard to use. And so it's really easy to sort of those sort of paper cuts really accumulate a lot faster for that user community. Than it would for, your typical computer scientist. So I was just wondering, can you, what sorts of risks exist, in your respective projects that you think people might hit if it starts being used in this community?
Go ahead.
Go.
Are you sure?
Yeah, please.
So the issue you talked about like you start using it, seems great, and then you hit a bug. This is definitely something we run into with Chapel with our users. Like those of us on the team have kind of learned where the well-trodden paths are and the safer areas to be and where you're sort of getting out into features that haven't been used quite as much, but that's not evident to a new user, right? And so we've had some users who've gone for years and have very few questions for us who use support issues because they happen to be on the paths that are well-trodden. I've got other ones who like instantaneously are trying things that are an interesting intersection of features that we haven't tried before. We're an HPC software team. We're not massive and we don't have as good of QA as like a mainstream software product might be. So I think one of the nice things about the Arcuda project is that it sort of separates these roles from, the person implementing the Arcuda features, if you will, in Chapel and sort of maybe dealing with some of that pain if they do hit some of those rough areas versus the end users interactions, which are kind of like, I'm using a Python library that just happens to be implemented in Chapel. And obviously that is only good if you're in the Python user world. Like if you're implementing things in the server, then you are potentially wrestling with these non-orthogonalities from time to time. So that's something our team's trying to figure out ourselves is like, how do we do better QA or how do we keep users more informed about which features are safer and more battle tested and which ones are still kind of on the cutting edge. I don't know if you were looking for specific feature areas that were, or.
Yeah, I mean, potentially, maybe. I mean, if there are certain, I think some bugs are just randomly distributed and
Yes.
there's nothing really to learn.
Right.
But I do think there are some things, sometimes like you interact with Python memory management in ways that like are slightly screwy or whatever.
Right.
Or don't necessarily do what users expect. Like I stuck this thing in a variable and it stuck around for a longer, and then oops, I filled up my entire machine's memory,
Right.
or whatever. So I don't know. I mean, are there any sort of like patterns of things that you notice?
So some things come to mind for me, and I'll turn the microphone over to others. So one of them is since day one, Chapel has had this really strong story on paper about sparse computations and sparse arrays. But those features have never really received very much attention. So that's an area of the language that I only send the bravest of users into, and anybody else I'll kind of warn them away from. It is an area we've been working on beefing up recently to try to bring them up to snuff with the rest of the language, but I think sparsity is problematic. At some point, somebody started writing a linear algebra library in Chapel, and someone goes, oh great, they've got linear algebra, and the linear algebra library is very, very malnourished. So that's another kind of area that I warn people away from. And if you need to do linear algebra and you're not willing to write the routines yourself or call out to BLAS or LAPACK or something like that, then that would be something to be wary of. And then the Julia talk had the sort of whole array computations, right? Like no loops. So we've got that kind of syntax as well. And the performance is great for 1D arrays. And there's this performance cliff for 2D or higher dimensional arrays. If you say like A equals B plus C, that we really need to address. And you can get around it by writing the for all loop. It's not a sequential for loop, but the sort of loop-based form of that. But the fact that sort of the whole array form has this performance cliff is really regrettable. So those are three kind of big examples I feel like users hit with some frequency in Chapel.
I'll hop in next. So Dragon, a lot of the kind of things that users write, if they're not just taking multiprocessing code and spanning nodes, is are kind of like the classic like asynchronous problems, right? That you're writing an asynchronous workflow, things happen in orders you didn't expect it to, and sometimes you think you have it right and you get it wrong. And so you can leave like a process, your runtime won't come down because a process is sitting in like a queue.get, and one worker grabbed 2 items and one worker saw no items, so that never exited. So things like that are kind of areas of complexity in the Dragon runtime. There are tools to help that. we have like some verbose logging to help with that, find those errors. Other things is, you can start on a single node. You can start on your laptop writing, straight multiprocessing code and kind of flush out some of those issues in a place where you can iterate really fast. You're not using valuable time on a supercomputer. And then you can take your code where you kind of have a lot of those issues worked out and take it to a supercomputer. So
Yeah, I'd say from the Rust side, I can kind of reason about this from two different aspects, the Rust side and the Lamellar side. And Lamellar encompasses all the Rust issues. The biggest one is just fighting with what's called the borrow checker. If you've never programmed in Rust before and all of a sudden some of your common ways that you access memory can't be proved safe, you sometimes just want to chuck your laptop at the wall, because fighting against that compiler, sometimes it really does feel like a fist fight. So, there's definitely a startup time for people to get up and running in Rust. And then from kind of more of the Lamellar side, because we see it, but maybe more a distributed environment side, I would say two things that are very hard are small messages and, doing automatic aggregation can solve some of it, but it doesn't solve everything. And then very related to that is a regular memory access. So if it's like something like a graph algorithm, those are also very hard. They're actually, the algorithms themselves tend to be very beautiful from the user standpoint, but then implementing that on an actual machine and through a runtime, that's a very difficult problem to get right and get fast. So.
Any comment from Julia?
Sure. I've had plenty of time to think about this. I wish I could say no photons. In order of least favorite things, the garbage collector. That's why I'm also crustacean. Yeah,
Crustacean,
yeah. So the garbage collector is a necessary evil. Also, sometimes these foot guns are like, yeah, but you still need a gun. Right? I really like the idea of provable correct memory access, but that requires you to think about your algorithm in a different way, which goes against sort of my most important criterion, which is don't tell the scientists to rethink their problem. So you have to have a garbage collector, and the Julia garbage collector is garbage. And people are working on it, and it's getting better. So if you look at version 1.10, 1.11, and 1.12, you'll notice that it's actually got miles better. And that's really because at 1.9, it was so horrible that people were really angry. So garbage collector is one thing. The second thing is, and this is more of a foot gun because JIT is not a thing that people are used to. So one example that I really like is Julia actually stores its JIT to a cache. So, and that cache lives in your home directory by default. And then this is a fight I have with everyone. Your user goes and makes it work on a laptop. It works fine. It works on a login node. Great. The home directories on the compute nodes are different. And all of a sudden, the thing just hangs. They can hang for 24 hours because of the way that homes are resolving the concurrent writes from many nodes, JITting the same function and trying to write to the same cache. There are ways around it. So this is like one of those examples of if you just read the documentation, then you will know this is how you do it. Right. But it's not a default, and this is why I fight with people. It's like, well, this should just work by default. Right. And the last thing really is again something I can get that should just be documented better. There is ways to write slow Julia code, which is still faster than Python, but it's still slower than Fortran or C. And then there's ways where you can compete with Fortran. And it requires you to know where to do, like where you turn off bounds checking, for example, where you turn off the garbage collector. And so those things, just knowing where to turn those on is a little bit of a dark art. And I wish that was documented. Not better, just I wish it was documented.
So Maybe I have, maybe for Julia and the last, advocates, I have just quick question. So I know these two languages have a keyword to make some operations unsafe. How much do you recommend for performance heavy users?
So I think generally from most Rust applications, you're better off writing idiomatic Rust without dipping down into unsafe, and you'll likely get better performance. Unsafe really should be reserved for interacting over a foreign function interface to interact with C or C++ libraries. Or if you're 100% sure that you need to do manual pointer arithmetic. But I would say for 98% of the users, they shouldn't be touching the unsafe keyword. Now, that's saying that as someone who uses it almost every every source I have, because I have to interact with such low level memory. But I don't want anyone else to use it,
Well, that's kind of the beauty of LAMLR, right? Is that you're abstracting those unsafe things into
Yeah.
your darks and your arrays
Yep,
and things like
exactly.
that, right? So
Yep.
the client doesn't have to.
Yep, that's the goal at least,
Right,
for
right.
sure.
I think that's the same sort of answer for the Julia world. I use, there's the favorite one is inbounds, right? It just basically says, I know what I'm doing.
Mm-hmm.
Most of the time I don't know what I'm doing, but my job is to sort of not know what I'm doing.
Yeah.
So I try to hide that from users. I sound like I have fights with everyone. These are all nice fights. Passionate disagreements. There's one flag in Julia. You can launch Julia to make everything unsafe. I think that's a horrible idea. And for some reason, a lot of HPC users think that's a wonderful idea. Because then they don't have to reason about every single snippet of code and explicitly mark it as inbounds. That's what I love about Rust. It's saying like, you want to do it this way? Do it this way.
Yeah.
But seriously, you're gonna have to work for it.
Yeah, you have to opt into unsafety in Rust, and then you have to be very explicit about it.
No. I wish they were better in Julia, but most of the Julia users would disagree with me.
Thank you. Any questions on the comments? To the panelists? Yes.
Question on the Kupai numeric. You said you were built on the legate foundation. I'm not familiar with legate at all. Can you give like a brief, like how much of it comes from the lower level versus what's added in Kupai?
Right, so Legate is the thing that provides the distributed array abstraction, which is called a logical store, which, it's a first class value that contains partitioning information. Not immediately something that the user needs to worry about, but it's something that the middleware layer has to reason about based on what the needs of the higher level library are. So if you're doing the example I like to use is like NumPy sort is one that you have to provide, and unique or something like that returns indices, and there's a contract that those indices must be returned in C order. So if we need to provide that guarantee, then that restricts the partitioning that we can do. Like we can't just tile the array because then and just return the indices, because that would give them in a wrong order potentially. So we can only partition row wise. So that's something that the Kupai numeric code tells Legate, partition this, or I'll accept a partition that's row wise. It doesn't matter how. But if it's not row wise, then you know about the partitions, figure it out. Return me a partition that works for me. So that's kind of the contract between the libraries, and Kupai numeric will build the matrix multiplication, and it will make sure that the will describe to the Legate, to the underlying execution layer, that these partitions need to align in this way so that the results of the math model go where they need to go. So so the Legate layer provides the synchronization, data dependency, partitioning, choice of partitioning, and where the computation runs. And then the actual numerical algorithms are higher.
Thank you. Any other comments? I have another question. So in this workshop, we have already discussing lots of topics, but I think the major interest of us in this meeting is integration of high performance computing and scientific equipment and facilities and plus emerging AI, machine learning together. So what tool ecosystem in the language or programming model you are defending is what is basically what kind of tool system supports the what are the missing features needed for your framework or language, your language or framework you are defending? I don't think you can say everything is there. If not, you can be honest to say, okay, something is missing.
I think it's easy for Rust. Their GPU story is basically wrapping CUDA kernels, which is fine. I think everyone who's developing Rust would love to see something that is more rustic from the programmer's point of view, that maps down through LLVM and the intermediate representations onto the GPUs underneath. So I think that's probably a component that's missing. And then, I think because the language is new, the AI story there is growing, but it certainly isn't as developed as a lot of these other languages. So one kind of goes with the other right now. So, I think those are probably the two biggest, just lack of support right now.
Brad?
Yeah, I think something that's really become very clear to me today is the importance of the computing at the edge and the ability to handle streaming data. The streaming data I sort of anticipated coming into this, but the at the edge computing, not so much. And I think so the streaming data I feel like is something that one could create a story for within Chapel or CUDA, but we don't have that today. So I feel like that's something that would require more investment. Today we're used to reading in data from Parquet files or HDF5 files or whatever. And I understand that's also part of this community's workflow, but if you could go straight from the data into an CUDA data frame, like that seems like that could be better. So that's something that occurs to me. On the AI front, people have done some AI codes in Chapel, but it's really hard to compete with like PyTorch, for example. And so in practice, what we've been doing is calling out to the C++ interface to Torch. And that gives you a capability, but it has not yet been very well integrated into Chapel such that you can just call it like from a standard module. And a lot of our standard libraries do wrap kind of libraries in other languages, right? We don't reinvent everything from scratch. So I think sort of a proper AI module in Chapel that sort of wraps existing capabilities and exposes those to the user is something that, again, people have done that manually, but I think we could make that a nicer experience.
And Corin and Manolis, do you have any comments?
Yeah, so I think that the way Dragon has approached these things, sitting on Python, being in Python, we get all of PyTorch for free. So I have a much easier job than some of these people up here. I guess I think we've really, as a project, have roots in simulation and AI. That's something that we've been interested in a long time, and that's something like in the slide I presented that I tried to call out. Facilitating data exchange between simulation and a simulation code, traditional CFD code, and a model you want to train or do inference on to replace one step of your simulation. So Dragon has a lot of stories around AI. I'm gonna say that it's not obvious to me because of the Python community. You can pretty much go and grab the tool you need if it exists already to implement what you want. Most of the AI stack is in Python, so it kind of is all around for you to grab.
How big of an issue is it? Sorry to interrupt. How big of an issue is it going between library to library? Is it all common data representation?
So it has to be serialized.
Okay.
So there's ways in there, we have some convenience functions mainly around NumPy because that's kind of the most common thing that you're passing between. So serialization for that between those to go between those frameworks, but that's about all that's extra additionally needed.
So for us, it's the same story as Brad, exactly. There's no, it's the NumPy API, it's some of these libraries, but we, it wouldn't be a great idea for us to try and redo machine learning, deep learning. So what's missing is some good integration with these AI frameworks. It's not gonna be pretty no matter what, just needs to be as less bad as we can make it. So we had someone asking, do you have AutoGrad? And well, I mean, if we're gonna have AutoGrad, might as well try and reuse these libraries instead of us re-implementing the whole thing badly. So integration with the AI frameworks, visualization is a big one that this group has brought up. People in this context have brought up multiple times. And I'm not a GUI, I'm not a UI person at all, so I'm not in any position to offer, suggest solutions here, but it seems like it needs to be a co-design. My limited understanding is that needs to be a co-design process with the writer of the code, because just trying to scale up your matplotlib calls is not going to be a scalable strategy. So you at least need to be aware of what you're trying to do and what you're telling us to do, because we've learned not to promise that we can make magic happen. Yeah. So and then making the system understandable to the end user, so they're not surprised. As Elliot has been using the system and is a power user, so he can kind of peer under the hood and understand things that are slow and things make sense. But not all users are going to be power users. So it's like, why this partitioning decision happened, and why did this data have to?
So Jada, that's kind of a follow-up for, I think your question is, what about tools for debugging and performance? Are they relevant to you? Do you need them? Or, I mean, that seems like a challenge maybe for everyone, right?
And I can continue talking. This is, yeah, absolutely. And then it's like we use the tools day in and day out, so we've gotten kind of nose blind to that. How these concepts are unfamiliar to everybody else. So do we have even internal internal debates like what like when we say, so I have to, I'm in a private company, and I have to deal with product managers who tell me performance is bad. Well, what does it mean that performance is bad? You try to run something that's unscalable. Who is it? Whose fault is it that it took 3 hours? Right?
Or maybe there is some magic bullet. They structured it
Magic
wrong,
bullet,
right?
right? And yeah, maybe better expert tools is the solution, but they're not gonna always work, right? You're gonna have the tools need to provide the information at the level that the users can use them, and then sometimes it's like nothing you can do. Sometimes all you can do is open a bug report and try something else. So
I just try to compare it to what we do in traditional languages, right? We do have some tools. Some of them are good at advising, where maybe you could make some changes to get better performance. Similar with debugging, right? You have some tools that might be able to help you narrow down in well-established languages. Maybe Python has some of this, but Python hasn't necessarily been focused on it. And then you have your backends, which, you want them to be invisible, but what if they're not doing what you expect?
So I'm gonna again say Julia has it all. No, but this is really when I started using Julia. The way you become a Julia user is someone in your office is a Julia user and doesn't stop talking about it. And then you listen to them, and then they show you an example, and you go like, "Oh, wow, that is cool." And so my version of that story was, you can interrogate LLVM all the way down to machine code if that's really the sort of, like, I don't know, you want to show off in front of a friend or something like that. But like most of the time, you can go through every single layer of the translation from your code all the way to machine code. So that's very much a tool for an expert.
And that's built in, you're
And
saying?
that's built into the language. And so, there's, if you know what blogs to read and things like that, so the community could do a lot more work in just aggregating this into, for example, NSAT Compute has all of these, and NSAT systems tell you all of these helpful first guesses of what you might try to do based on the performance data. And for like Julia, what we're sort of missing is, we can look at LVMIR, and if you've been staring at that stuff for a year, at that point you're like, oh yeah, that's the problem. But like getting there takes some time, and just getting better advice there. Also, the error messages, thanks to Rust being like showing us how to do it properly, the error messages have gotten way better. But actually, I think because the question was what was missing.
Yeah, what is missing?
What I would really love, and this is something that's free or actually saves money for all the vendors. Stop sucking the oxygen out of in the AI space. It's probably hard to do because you all want to make money, but there's so much money going into PyTorch and the Python ecosystem for AI that it's just impossible to compete. So you're always going to get a shinier, much more polished product. My experience with the Julia AI ecosystem is that once you get rid of all the weird edges, you can create some really awesome, cool stuff, like do autograd through an MPI call because you've got LLVM on your side. That project, by the way, is called Enzyme and Reactant. Like Enzyme is the C version, and then Reactant is the Julia version. But it is full of rough edges, and most of the time it will just leave you frustrated because you're used to how polished the NVIDIA products are, how polished PyTorch is. And so that lack of polish is really, a lot of the money goes into polishing things. And the less, I was being a bit snarky there with stop taking the oxygen out of the room, but maybe like invest in other languages because monoculture is bad. Monoculture is bad for science. And so seeing similar investments would be really nice. Fun fact, Julia is largely funded by SML at the moment, so the edge stuff actually works surprisingly well. So I've seen a paper where someone put Julia on a drone. So yeah.
All right, it is almost time. Maybe we can take final question and comment.
Well, I'm wondering if we should hear from, some of the people who are closer to the science in this room, like what would it take to use one of these systems in your actual production environment? Like Nick, if you were going to use this hypothetically in CCTBX, what would it take to get you there? Or
I have a related question. It's also this thing of what would it take? I think there's actually a much larger gap than we realize between using them and figure out what's wrong. Because most of the time your code will run without an error that you can read, and you will have no idea how to find out what the issue is. And so is there any way to actually even build such a tool? Because you would need to know things like data layout, is it C ordering, Fortran ordering of your data? And then how are you reading them? How are the channel ordered? Like, how is your arithmetic intensity? And so is it even possible to have a tool that will at least warn users that something is inefficient? And I think that would be because no one will have perfect knowledge of both domain of expertise, right?
I think there are multiple layers, multiple answers. Like the answer is multiple layers to that question. At the very bottom, Rust addresses some of that from a memory safety aspect where it will just tell you, you're trying to access these things in a non-mutable way, or so the language itself will prevent some of that by just not compiling. I think There probably needs to be some layer at a runtime layer that can reason about data layouts or, data accesses. And maybe, I hate saying this, but maybe there's an AI component that goes into that is reasoning about how data is being accessed and based on previous models can say, historically, this has not been fast or something like that. Maybe there's some tool that we could create that now. Do I really want to see that? I don't know. So I think there's ways, the language itself and the compilers themselves are part of that question or a part of that answer. The runtime layer is a part of that answer, and then the frameworks on top of that are probably a part of that as well.
Any comments? Okay.
Well, I wanted to answer your question. I mean, the goals that I set, 2 kilohertz data processing, that's a low bar, right? We're gonna want to go beyond that. And it's clear to me that we're eventually going to use GPUs for our data processing. But these results my go-to instrument would be PyTorch. But I think it was your graph about what is the performance of PyTorch. Was it you or?
Oh, yeah, that graph, I was shocked about that.
That was shocking. And it's actually I have a little experience in PyTorch, and it's always disappointing. Because, I have to marshal the array and then send it to the GPU, do a little bit of addition and then come back. Maybe Haiku numeric has that optimized already. So yeah, I can see that. I mentioned in my talk earlier that there are other steps in the data processing we haven't even attacked yet. So yeah, there's a lot of potential, but not maybe for Julia, because we have 20 years of development in CCTBX.
No, see, that's actually the point. What you were telling me basically is maybe the meta comment I would have to address Elliot's question. As a community, and this is the hardest problems are social, right? If we can all agree on a same common packaging and ABI standard, then we can use whatever languages we want. And we can use the 20 years experience of CCTBX, but someone might come along with like a Rust module.
Rust doesn't even have a stable ABI, so.
But ABI standard is very important, especially considering container or considering.
Well, is the code ABI what matters, or is it the data? Right? I mean,
it's a data
right? I mean, we're
ABI.
talking about like Apache Arrow or something vaguely of that ilk, right? Like, I have this array with these fields and this layout, and I'm going to hand it off to you in some fashion, right?
Yeah. I mean, like when we're talking about making foreign function calls, that serialization isn't involved in that at all. And at the same time, also, we're packaging is something that's death by 1,000 paper cuts. It's not bad enough to fix, but like every time I have to fix a damn Conda environment, I would get years back. So yeah.
I was going to mention, since data layouts came up a couple times here and over here, one of the key principles in Chapel from the beginning was that the language and the compiler should not sort of determine what the data layouts are. So we have a first-class concept of index sets in language, and we have arrays that can be mapped from those indices to elements. But the specifics about how is it laid out in memory, is it row major, column major order, is it tiled, does it use compressed sparse row or column? All of that is kind of outside of the language, and you as a user can actually define your own array data formats and plug those in. And we think that's really crucial. And one of the reasons for those who followed the project for a long time, that it took us a long time to get the kind of performance you saw today, was because we insisted on building all of our arrays and our distributed arrays using the same mechanisms an end user would. So we wouldn't have this cliff between the things that were built in and the compiler knew about, and then the things that the user would write. So through a lot of hard work, we've gotten to the point where the language has been able to be sort of neutral to data formats and yet still turn out the kind of performance I showed today.
All right, any comments? All right, it's time. So thank you. Let's thank panel speakers again.